Okay, so today we're going to talk about genetic drift. We've already talked about this a little bit, so you should have some idea already. So, we've mentioned previously already that genetic drift is one of the mechanisms of evolution. Natural selection is another one, mutation and migration. We've spoken about natural selection and mutation and a little bit about migration. Now, this means that it actually affects evolution. So, it's a mechanism of evolution. So, genetic drift, essentially, in a nutshell, it's fluctuations in the gene pool due to chance events or random sampling. Now, we've spoken about chance events and how that affects a small population. I'll talk about what I mean by random sampling in the next slide. So, as you know, the smaller the population, the greater the effect of genetic drift. And this is because a small population is more susceptible to a random chance event occurring, which will significantly alter the gene pool and the distribution of alleles. Now, if you look in the picture down the bottom, you can see that if you have such a small population of beetles with green phenotype or phenotype and brown phenotype, a chance event happens, so they get stepped on, and a lot of the green gene is taken out. Now, this is genetic drift. Okay, so it's a reduction in variation. All right, so what I meant by random sampling. Now, we know that in every generation, some individuals, not by selection, so not by sexual selection, but by pure chance, may have more offspring and therefore have more genes being passed down than other ones. Okay, so these genes that are passed down in this case are lucky individuals. They're not necessarily the more fit individuals or the better individuals. So this also influences the gene pool, and as you can imagine, in a smaller population this has a much greater effect. In a large population this effect is very minor. So if we have a look at this slide, you can see here we have certain flowers that are reproducing. So let's say by chance these 4 red flowers and this 1 white flower reproduce. So 5 of the 10 leave offspring, which causes generation 2 to look a bit like the second picture. Now, by complete chance, only 2 of the 10 plants leave offspring in the next generation, and because it's such a small population, you can see that generation 3 is completely containing the red phenotype only. So the white phenotype has been lost due to genetic drift. Okay, so it's the chance occurrence that this will happen. It's nothing to do with selection. Okay, so in terms of genetic drift, there's actually a few effects that can occur. So the first one is the founder effect. Now, this is where genetic drift will cause a small population to be separated from the original population, which causes a new population to form based on this small founding population, so this small group that's been separated. Now, again, there's a lot of reasons why this might happen. Chance events can cause some individuals to be separated, or yes. So what happens in this case, as you can see in the picture, is that you have reduced variation. So you can see that the purple allele has been completely lost from the population due to the fact that such a small sample was taken to form the founding population. So this can cause issues. As you know, we like to have genetic variation as it makes populations less susceptible to diseases and such effects. Now, you can have a quick look at, sorry, I didn't mean to skip that so quickly. I hope you managed to pause that, or you can go back and pause that. Okay, all right, so here's an example of the founder effect. Now, I actually find this quite interesting. So in South America, we have the Afrikaan population. Now, part of this population was made up of Dutch settlers. So today, because we had these Dutch settlers come to South Africa, and there was a small population of them, so a small few colonists that colonized South Africa, we've had this founder effect occur, and this is because in this Dutch population there was a higher frequency of the gene for Huntington's disease. And we've spoken about Huntington's disease before. It's a really severe disease that causes both physical and mental degeneration to the point where you will die at a younger age than usual. So it's a terrible disease. And so now we've seen in South Africa that people with the original Dutch heritage happen to have a much higher frequency of Huntington's disease occurring. Okay, so you can see how it can be a negative, this founder effect reducing genetic variation. All right, number 2, bottleneck effect. Now, this in essence is where a disaster occurs. It causes a lot of the population to die off, and only a few survivors will carry the alleles, surviving alleles. Now, if you can imagine a bottleneck filled up with marbles, and only a few marbles can escape through the neck of the bottle. That's essentially the bottleneck effect. So you only have some surviving alleles, and in essence this causes reduced genetic variation, which we know will mean that the surviving population will not be able to adapt to new selection pressures as easily, and may not at all be able to adapt, which would cause the population to die out. And for example, climatic change, or if there's a shift in available resources. Okay, so let's look at an example of that. So you can see on the picture what I was describing with the bottleneck effect. So only a few little organisms can survive and escape from the deathly bottle, apparently. Now an example of this is the elephant seals. So in the 1890s, hunting caused the elephant seals to be reduced to 20 individuals. 20. Now their population has luckily increased and survived, and now they have a population of about 30,000, but because of this bottleneck effect, they're still affected in terms of their genetic variation. So they just don't have that same amount of genetic variation as they had previously, which again makes them more susceptible to diseases, less able to adapt, and all round we know that less genetic variation is no good. And that's it.